Okay, welcome back. This is 10.2, plane curves and parametric equations. Okay, I just want to play around a little bit with the formula for a line, the equation of a line. So hopefully this will go somewhere. If not, I apologize in advance. So let's say I have 2 points. Um, let's say let's make the y-coordinate over here. I don't know. 9, and then we'll make this guy 3, and then let's make this guy um, 4, and make this guy 2. Right, so I can get the equation of a line from this, right? So this formula, I need a slope and a point. So the slope is 9 minus 3 is 6, all over 4 minus 2 is 2. So our slope in this case will be 3. And then I go y minus y1 equals m times x minus x1. And so I plug this point and the slope in there, so I get y minus 3 equals 3 times x minus 2. So I get y minus 3 equals 3x minus 6, and then y equals 3x minus 3. Okay, great. What would happen then if I let x equal some other expression? So let x equal, let's say, t plus 4. Let's plug t plus 4 into this expression and see what we get. Then we would have y equals 3 times t plus 4 minus 3, which is 3t plus 12 minus 3, which is 3t 9, 10, 11, 12, right? 3t plus 9. So what we have here is a set of parametric equations for this line, believe it or not. X equals t plus 4, and then y equals 3t plus 9. If you don't believe me, we can actually plot these things, right? So may need a lot of room here. You know. So the point 2, 3, 1, 2, and then 1, 2, 3 is right here. And then 4, 9, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9 is right here. And so we have our line. I don't know if it went through the origin, but mine did, unfortunately. And then over here, we can look at t values, right? We say t equals 0 and get corresponding x and y values. So when t is 0, x is 4. And then over here, when t is 0, y is 9. Well, that's definitely on the graph, right? Because we had this point 4, 9. This is 4, 9. You plot that, you would get, 4, 9 is right here. Try t equals 1, and you get x equals, 5, and then y equals 12. Okay, so 5, 12, I'm guessing is also on the graph. It'll be up there somewhere. Okay? So yeah, it seems like I could always rewrite some equation like this with two new equations, and then kind of analyze the situation in this new setting. And each one of these has its own slope. So later on, you can kind of separate slopes out and write it in a different way. So you'll have like kind of an x formula and then a y formula, right? And then the x formula will have an x slope, so you can write x2 minus x1. And the y formula will have a y slope, so you could write y2 minus y1 times t, I guess. So we can kind of maybe write it like this. And then plus a particular point on that x point. So we could pick 4. And but in general, we'll say x1 and x2, or x2 and y2, or whatever you want. Okay. And then you kind of wonder, is that always going to work? You know, is this really like going to give you these two equations? So here's one equation, and here's the other equation, right? Let me write that. So x is equal to the x slope, x2 minus x1 times t, plus some particular x value. So say x 1, and then the y formula will be equal to the y slope, y2 minus y1 times t plus some y value. So let's see what we get, right? If I use the points from above, and let me use x2, y2, because I know where I'm kind of headed. Okay, so it doesn't matter for this next point as long as it's some point on the line. So my x is going to equal then x2 minus x1. So 4 minus 2 is 2, and then we have t plus this x2. Maybe I should just let me just use. I apologize. Let me just use x1. So x2 minus x1. So again, x2 minus x1, 4 minus 2 is 2t, and then plus, let's use 2. And then here, y2 minus y1, so y2 is 9, minus 3 is 6t, and then plus this 3 value. Okay. And we think those are going to be formulas for this line. Like we can just use those. And so are they? Well, you can kind of solve this guy for t, right? So x equals 2t plus 2 and solve for t. So 2t equals x minus 2, and then t equals x minus 2 over 2. And then substitute that expression into here. So you're going to get 6 times x minus 2 over 2 plus 3. 6 over 2 is 3 times x minus 2 plus 3. And that's 3x minus 6 plus 3. So y equals 3x minus 3. And so did we get back to where we started? Yeah. So if you remember here, I use the point slope formula to get that formula, and here I use these two equations where I kind of separated off the x slope and the y slope. Okay, so these are in general the parametric equations for the equation of a line, and you can parameterize pretty much anything so long as it's made up of a bunch of just straight lines at this point. In particular, you may have a three-dimensional scenario. So you have a particle running over top of this floor here, right? And it's running on the edges of the floor. So at time 0, maybe it's at this height, and then it goes up to here, and then it keeps running down and up and down and up until it gets to about right here. And then maybe it goes in this direction, so it starts going up and then down and then etc. Okay. And what you're going to be doing is sometimes you'll want to integrate over these lines, and you'll need to parameterize the lines to work with them. So you'll need equations for these things as you sort of work through the problem in order to figure out maybe the area of these peaks and valleys. Okay. So I need a formula for the sides of these boxes, size of that box, in terms of parametric equations. So let's look at a simple version of this where we just have a box and 4 corners of a box. So 0, 0. This point is 0, 1, 0. Well, let's go 2, 0, right? Let's make it a little bit interesting. And then 2, 2. And then this point is, what is it, 0, 2. And I want to parameterize this thing and get basically 4 parametric equations, 4 sets of parametric equations to describe the movement around this box. So I need C1, C2, C3, C4. So you can set it up and use the formula that I've introduced here, which may, probably not in the book, right? So our formula, which I seem to have, oh, it's on the other side of this paper. It's this formula, I think, that we'll use to generate these curves. So for C1, what do I have? I have x equals the slope, the x slope. So the x slope is just x2 minus x1, so 2 minus 0, which is going to be then times t, and then you add in one of the x points, but the x point you use has to be associated with the y point that you're going to use down here. Okay, so let's use 0, 0. That'll be the easiest. No, I want to end up, no, 0, 0. You want to use the starting point. Okay, if you use this point, then your orientation will be screwed up. It'll actually go out here. So I also want to make sure that I'm running from time t equals 0 to t equals 1. Okay, so that's a further restriction. In order to pull that off, I'm going to let this point over here be the 0, 0. So plus 0, if you wish. And then the y version will be the y slope. So 0 minus 0 is 0. And then plus the y coordinate. So this crap, this isn't going to work, is it? No, it will. Okay, so you end up with this system equaling or being 2t, and then y just equals 0, right? So you can check that at time 0, you'll have 0, 0. When time is 1, you'll have 2, 0, which are the coordinates we were after. Okay, so let's go after C2 now. So C2 will be, we have x equals the x slope again, so 2 minus 2 is 0t, and then plus, we want to use the starting point. So 2 is our starting point, and then y will equal the slope. 2 minus 0 is 2, and then times t, plus the starting point. We'll have 0 there. So this will equal x equals 2, and then y equals 2t. And again, I'm just going to use t equals 0 to 1. Turns out, for later purposes, it's fine to always have the same interval, because you'll be dealing with integrals, and the integrals will be separated. So if you always just use 0 to 1, it really won't mess things up too much. If you want to move it, all you have to do, I believe, is just to shift the t value. So maybe make it t minus 1, and then you could go, and t minus 1 here, and then you could go from 1 to 2. Okay, so at time 1, the t expression would be 0, and then at time 2, the t expression would be 1. So when t is 0, you get 2 comma 0, which is this point, and when t is 1, you get 2 comma 2, which is this point. Okay, let's get C3 now. Okay, so I use the x slope for C3 is going to be 2 minus 0, which is 2, but it's this point is the second point, right? So it's actually 0 minus 2, which is negative 2 times t. And then my starting coordinate is x value is 2. And then y equals 2 minus 2, which is 0t. And then the corresponding y coordinate is also 2. Okay, so our C3 system, x equals negative 2t plus 2, and then y equals 2. So at time 0, I'll have 2, 2, which is this point. And at time 1, I'll have negative 2 plus 2 is 0, 2. So at time 1, I'll be at 0, 2. Okay. And finally, C sub 4. Going back down this way on the box, I'll have x with x slope is 0 minus 0, so 0t, and then the x coordinate is 0. And then y slope is 0 minus 2, so minus 2t, and then the starting y coordinate, the starting x coordinate, the starting y coordinate is at 2. Okay. So at times, so let's rewrite it. So x is equal to 0, and then y is negative 2t plus 2. So at time 0, we'll have 0, comma 2, which is this point. And then at time 1, I'll have 0, comma 0, which is back to the start. So congratulations, you parameterized a square. So that's kind of where you're headed in Calc 3. You want to be able to parameterize basically any kind of curve. And this section gives you an okay introduction to that concept. Okay. All right. There's going to be kind of this movement from parametric equations to rectangular coordinate systems and then vice versa. The book takes some time talking about cycloids, which is an interesting thing. It's related to astronomy, I believe. So a long time ago, the astronomers didn't know that the planets were orbiting the sun, and they'd look up in the sky, and here's the path they would see. It'd be kind of crazy like this, and they wanted formulas to model these patterns. So maybe there'd be epicycloids and stuff like that. So the formulas they would use would be these crazy epicycloid formulas, and they would actually predict the occurrence of the movement of the planets up in the sky. But then, obviously later on we learned that these things are orbiting the sun, not Earth, and it made everything much, much simpler. We didn't have to worry about these issues. But the cycloid problem is put in the book, and I think the cycloid problem is this is kind of an epicycloid. It's a kind of cycloid. The cycloid in the book, though, may be associated with other problems like pendulums or something. I'm not sure. Okay, but anyways, there you go. There's a little bit of astronomy history from what I remember. So, you can say it for what it's worth. Anyways, let's continue on then and just look at maybe some problems in the book here. So sketching these things first off. So let's take a look at an example. Here I have a parameterization of a line. So x equals 3 minus 2t, and then y equals 2 plus 3t. I want to go from negative 2 to positive 2. Okay. So to graph these things, instead of just having x and y, now you have t and then x and y. So you go t, x, y. So just look at negative 2 to the 2. So negative 2, negative 1, 0, 1, 2. And plug these values into these expressions, and then you can plot the points in the rectangular coordinate system, the xy plane. So negative 2 into x, you get 3 plus 2, 3 plus 4, sorry, is 7. And then you have an x slope of negative 2, so this is always going to be going down by 2. So this would be 5, 3. If you plug 0 in here, you get 3. So it works, but I'm just using the slope 1 and then negative 1. Okay, then you can get the corresponding y values. So when it's -2, you get 2 plus -6, which is -4. And then when you plug in -1, you get 2 minus 3 is -1. So the slope here this time is +3. So go up 3 every time. So this would be 2, and then 5, and then 8. Okay, so we can go ahead and plot this. So 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4. So that's at time t equals -2. And then we have 1, 2, 3, 4, 5, -1. So that's when t is -1. And one beautiful thing about these parametric equations is you can designate a direction on a curve. So in this case, because I went from -2 to -1 here, the direction is counter to what we intuitively think. So it's not going in this direction, we're thinking this direction. Okay, so t equals 0. I get 1, 2, 3, 1, 2, 3, 1, 2. So I'm going in this direction now. I mean, it's going this way. Okay, 1, 5, 1, 1, 2, 3, 4, 5. And so it's still going that way. And then 0, etc. Right? It's going to go all the way to -1, 8, -1, 1, 2, 3, 4, 5, 6, 7, 8. So it's going to go right to there. So this is at t equals 2. Okay, great. Let's work with converting back and forth. So it's basically, it comes down to eliminating a parameter. And I kind of already alluded to this in my primary example at the beginning of the lecture. So parametric into rectangular metric. Right, so you're going to want to solve for t, substitute, and then adjust the domains. So first, the first method is eliminate the parameter. Okay. So for example, going back to the first example I was playing with there, x equals 3 minus 2t, and then y equals 2 plus 3t. We can solve for t in this equation. So x, let's go with 2t, add 2t to the other side, and then subtract x from both sides. And divide by 2, so t equals 3 minus x over 2. And then take this guy and plop him in there, eliminating that parameter. Okay, and then it'll be in terms of y and x. So y equals 2 plus 3 times 3 minus x over 2. And so we get 2 plus 9 halves minus 3 halves x. So y equals -3 halves x plus, so this would be 4 halves, 13 halves. Okay, so that's what we're used to. The parameter was they said to go from -2 to 2. So to change the parameter values into x values, what you do is just substitute in for t in terms of x. So you have 3 minus x over 2. And then solve this compound inequality for x. So multiply all 3 sides by 2. Subtract 3 from all 3 sides. And then multiply by x, -1. And you have your new restrictions. Okay, so eliminating the parameter, let's look at another one, number 10. So x equals the 4th root of t, and then y equals 8 minus t. So this time it's the parametric equations for something other than a line. Here we can solve for x, or solve for t rather. So I want to take the 4th power on both sides, and you get x to the 4th equals t. And then take that guy and sub them in here. So you get y equals 8 minus t, which is now x to the fourth. Okay. So it's basically a kind of parabola that's flipped upside down and then shifted up 8 units. Okay, so picture, and we have to be a little bit careful because there is an implied domain for the t values here. Because we have a fourth root, I can't put negatives in the t, so this implies subtly that t needs to be greater than or equal to 0. Okay, so when t is 0, and it's going to imply x needs to be greater than or equal to 0, right? So x to the fourth needs to be greater than or equal to 0. In other words, x to the fourth needs, x just needs to be greater than or equal to 0. So anyways, it's flipped upside down and shifted up 8. So 1, 2, 3, 4, 5, 6, 7, 8. And it's a parabola type looking deal. And I believe the orientation is in this direction. Okay, if you're not sure, just put in some t values. So t equals 0 will give you x is 0 and y is 8. At t equals 1, so this is t equals 0. At t equals 1, you'll get x is 1, and then y is 7. Okay, so 1, 7, t equals 1, and certainly it is going in that direction. Okay. So when you're graphing these, you do need to indicate the direction of travel on your curve. Okay, so eliminate the parameter just via, I don't know, what are we doing? Solving for a variable. This is one method to accomplish that objective. Other methods then, using basic trig formulas. For instance, the sine squared theta plus cosine squared theta equals 1, or the other variations of that theme. Right? So tan squared theta plus 1 is secant squared theta, and then 1 plus cotan squared theta is cosecant squared theta. Okay, so let's see that in action. This is example 3. Our set of parametric equations, x equals 3 cosine theta, and then y equals 4 sine theta, and our parameter is varying from 0 to 2 pi. Okay, so again, it's not an equation of a line. It's maybe not clear. It's not clear what it is, but you can solve for cosine and sine and then substitute it into this expression. So I solve for cosine in terms of x. Cosine theta is equal to x over 3. Solve for sine in terms of y. Sine of theta is y over 4. Right? And then plug this material into this first equation. So we note sine squared theta plus cosine squared theta is equal to 1. In other words, y over 4 squared plus x over 3 squared is equal to 1. And then we know from the last section what kind of object that is. It's an ellipse. Okay. The A value is 4, the B value is 3, center is 0, 0. So it looks like this. We need to figure out the orientation, so you can do a table to figure that out. So when theta is 0, x is equal to 3 times cosine of 0, which is 1, so x is 3. And then y is equal to 4 sine of 0, which is 0. So when theta is 0, I'm at 3, 0. And then when theta is pi over 2, I get x equaling 3 cosine of pi over 2 is 0. 4 sine of pi over 2 is 4. So I'll have 0, 4 when theta is pi over 2. In other words, it's this orientation. Okay. You can do other variations on the ellipse using these formulas and get the hyperbola. In particular, for example, let's say x is equal to 2 tan theta, and then y is equal to, my pen died, y is equal to, I don't know, just secant theta. Okay? And then you could solve for tan and secant and plop them into this formula. Right? So you have tan theta is equal to x over 2, and then you have just y is equal to secant theta. So tan squared theta, which would be x over 2 squared, plus 1 equals secant squared theta, so y squared. And then you could get the x squared over here, so you have y squared minus x all over 2 squared equals 1, and you have a hyperbola, right? So in this case, the a value is 1, the b value is 2, the c value is square root 5, it's about 2.2 something, right? Then you can come over here and draw out your scenario. So a is 1, center is at 0, b is 2, so I got my box. The foci are at 2.2, so 1, 2.2, 1, 2.2. And so let's get my asymptotes in there. And my curve will look like this. Probably the hard part then is figuring out the orientation. You have to pick out values on the two particular branches. Okay? And there's issues with the formulas in here. You're kind of jumping from branch to branch. So let's take a look at theta, and then we have our x and y. So you want to pick two intervals of 2 points each where you know these functions are both continuous. And so for tan, it's always continuous from negative pi over 2 to the pi over 2, and so on. For secant, that's just 1 over cosine, so it's going to have continuity and the same kind of intervals that tan has continuity in. Okay? So you could pick 0 and then pi over 4, and then jump to this next interval from pi over 2 to whatever. So we'll say then we can't use pi over 2, but we can use, so here's my unit circle. And there's an issue at pi over 2, so we could use 1, 2, 3 pi over 4, and then pi, I believe. Okay. Just make sure I'm not accidentally just sitting in this guy. So pi over 4, and then I'm skipping this, and I'm using 3 pi over 4 and pi. Okay, I think that'll do us. Okay, so let's go to then plugging in. Tan of 0 is just 0. And then secant of 0 is going to be 1 over cosine of 0, which is 1. So my first theta 0 is at 0, 1. It's right here. Okay. And then at pi over 4, tan of pi over 4 is 1, so this is 2. And then secant of pi over 4 is 1 over radical 2, so this is 2 radical 2. All right, so 2 and then 2 radical 2 is going to be on here, so this first curve seems to have this orientation. Then I jump to the other branch at 3 pi over 4, so tangent of 3 pi over 4, cosine is negative, but sine is positive, so it's going to be negative 1. Negative 2, sorry, because it's 2 times negative 1. And then secant of 3 pi, that's going to be negative radical 2. right? So -2 and then negative radical 2, or yeah, is going to put me down here. And then the next point at pi, tan of pi, sine over, whoops, so I can't use pi. That's a bad news place. It shouldn't be. Sine, oh, it's sine over cosine. So it's 0 for tan, sorry. And then secant is 1, so that would be, secant is negative and that at that position. So 0, -1, so 0, -1. In other words, this branch seems to be going in that direction. Okay. Okay. The last section then is kind of doing rectangular to parametric. So 2, 3. There's always a very quick way to accomplish this. For example, if I have y equals sine of x, you could just let x equal t and then y equals sine of t, and that gets the job done. So another example, if you have y equals x squared minus 3, you could just let, again, x equals t, and then y equals t squared minus 3. That'll do it. Okay. Summarize. So let's just make up a new one. So this is like 56. Y equals 2/3 x minus 3. And then I want, when I'm at t equals 2, to be at the point, and you can just use whatever you want, 3 comma -1. Okay. Okay, so what did I do? For x, I said I want my slope to be from here. So this is y slope over x slope. Okay, so the x slope is down here, so it'd be 3 times t plus some unknown b value. To get the b value, I use this point, right? So when t is 2, I get an x value of 3. So 3 equals 3 times 2 plus b. In other words, 3 equals 6 plus b. In other words, b equals -3. So my x formula is 3t minus 3. And certainly check it. When t is 2, you get 6 minus 3, which is 3. Okay? Then plugging this formula into here, I get y equals 2/3 times 3t minus 3 minus 3. Distribute the 2/3, so y equals 2t minus 2 minus 3. And then so y is 2t minus 6. Okay. So I can handle it that way. It seems like this section is kind of disjoint from the Calc 3 version of all these parametric curves. And the big reason is once you get to Calc 3, you're going to have you'll be dealing with vectors, right? So in the vector form, all you're doing is kind of rewriting these stacked over top of each other. So the vector form would be xy equals the x slope and then the y slope times t, and then plus this particular point that we care about. So the x point and then the y point. Okay? But you can see the equations here. This is the x formula from here, and this is the y formula from over here. Great. Let me look at the cycloid then. The cycloid, honestly, in Calc 3, I only saw it come up once, and it was in one of the homework exercises. So out of the thousands of homework exercises that I went through in Calc 3, I only saw it used once. I assume if you went into modeling with equations, maybe you would use it there. I've not really used it. But like I said earlier, though, it probably comes up if you're studying astronomy and maybe the history of physics or something. So anyways, at cycloid, what do you have? You have a curve traced by a point attached to a circle, and the circle is rolling. Okay? So you have this this sort of hemispherical object, a curve going on after the fact. So the curve is traced by a point P on the circumference of a circle. Radius A, rolling along a straight line. So there's all these curves. You can imagine making up some really creative curves, like if you have like a BMX rider and he's doing all those crazy tricks and stuff. Imagine that the wheels are covered in chalk, and that as the BMX driver is riding around, he's leaving a trail behind him. You can actually find mathematical models to model some of those curves, right? If he's doing one, maybe that's continuous. And I saw it online. There's like a French encyclopedia of curves. It's all in French, but it has you can translate it obviously, but it's like a huge encyclopedia of all these curves. I'm sure cycloids are in there. You might want to look that up if you're super interested in it, but probably not, right? Anyways, the parameter in this case, and this is the cool part, you kind of define your parameter to just be something like the angle the wheel travels in a bit of time. So you can be creative and make up your own kind of curves in this way using geometry. So the parameter we're going to call theta is the measure of the circle's rotation. Okay, so the picture then of this is following. Here is the radius of the circle is A, and then to the top of the circle would be 2A. And I always screw up the picture. I'm hoping I don't mess it up. So here's my circle, and it's rolling in this direction, and there's a pen sort of attached to the circle, like right here. As it rolls, it's going to trace out this hemispherical type repeating pattern. So let me try to draw the circle here, or sorry, the pattern that's being traced out. Okay, so it's going to go something like this, and then keep on repeating. So it's going to bounce up off there. We need to sort of locate a bunch of points to help us construct the parametric equations. I'll just note, going from here to here, you can think of it as if it's a roll of paper and it's unfurling itself, right? So you kind of think of this thing as kind of like a piece of paper unfurling as it rolls. So you can measure out how far it goes by unrolling the paper. Okay. So the distance then it travels, if you're starting, you know, with the point right here and then it's traveling around, it's as though you're unraveling the circumference of the circle. So as you start down here and then it goes full circle to get back here, this distance is just the circumference of the circle, which is 2 pi r. In this case, r is a. So this would be 2 pi a comma 0. To get to here then must be half the circumference. So it's 2 pi a all over 2, which is pi a. And then the diameter of the circle is 2a. So that point there is pi a comma 2a. We want to locate a bunch of points in here and then zoom in on it. So I need to do some construction. Here's the center of the circle. It's going out to there. There's a bunch of points. Okay. The theta value is going to be this angle here, this theta angle. We have O, B, D, C, this is A, and then this is a point on the circle P. Right? We need a formula for the x and y coordinate of P. And so we can get that by kind of doing differences and sums of these other lengths, right? So the first length for x is this OB distance. And this OB distance we're going to be able to get by noting that OB is really the difference between OD and BD. And we'll be able to find those two lengths. So first off, what do we want? We desire this x coordinate will be the distance between OD, the difference between OD and BD. Okay? And then for the y coordinate, that's this height, okay, which is BP, and we'll be able to figure that out by adding BA and then AP. Okay? So this will be BA plus AP. Okay, so we need to figure out all of that, and we can use geometry to do that. And we'll zoom in on this picture here. Okay? So we note then this picture kind of zoomed in. We have two parallel lines basically. So here's the center of that circle, and it goes over to P. Here's my A, and we have a right triangle sitting there. All right, there's my angle theta, and we have B and D down here. Okay. So also A right here. So what am I trying to get at? I need, first off, BD. Okay? So this length here. OD, this length from here to here, sorry, this length from here to here, I can kind of get by considering this length of the circle. Okay? So I'm going to have to I'm going to have to work a little bit to get OD. Okay. So OD and BD are kind of issues. I need to get both formulas for both of those right. So BD is really just AC. So if I could figure out AC, I'd be in a good place. Using trig, I note that AC must be equal to, well, I'm going to need to know this angle here, this APC angle, because AC will be basically, you know, adjacent all over hypotenuse. I'm looking, there's a mistake in my notes I'm worried about. Okay, I don't know this angle. Okay, so that's kind of an issue there. I do know this angle though, right? I do know this angle is the same as this angle because they're opposite interior angles, right? And then this angle right here, because this angle and this angle add to 180, must be 180 minus theta. So let me write that somewhere. That angle there is 180 minus theta. Okay, so working with this angle, I can get AC using trig. AC is the opposite side of this angle here, so that's what I want. The opposite side of this angle is so AC is AC all over this length here. This length here is just the radius of the circle. So from here to here, that's just the radius, and we know that's A. So AC all over A is equal to the sine of 180 minus theta. Okay. 180 minus theta is exactly equal to sine of theta. Okay. So I have that AC is equal to, if I multiply both sides by A sine of theta. Okay. Great. So so what? Well, now I can say that I know what BD is, because AC is the same as BD. So for the X formula, now I have X equals OD minus this formula here, a sine theta. I don't need to go any further. Right? So minus a sine of theta. Okay, if you're not sure why sine of 180 minus theta is equal to sine of theta, you can always do sine. So sine of 180. 180 is just going to be pi minus theta, and then that's equal to sine of pi times cosine of theta minus sine of theta cosine of pi. Sine of pi is 0, and so you have 0 minus cosine of pi is -1, so -1 times sine of theta, and of course that's equal to sine of theta. Okay? So that's why that's true. What else? I need that OD formula. So to get the OD formula, I note that this distance here is the same as this distance because it's kind of that unraveling that happens. This picture isn't really to oriented, scaled correctly, so it looks like this is longer than this, but they're actually the same distance. So if I can find the arc length of this portion of the circle, I found the distance from O to D. So I need an arc length formula. So for OD, I need that arc length formula. So what was the arc length formula? The arc length formula said that, so if this is my center and I'm worried about this angle theta, standing room only was the formula, right? S equals R theta. So in our case, S is equal to R, the radius is A, and then times our theta angle. So OD is the line, the line segment OD is equal to the arc length from D to P, which is equal to A theta. Okay? So we basically then have the formula for X. So X, the formula for X is just A theta minus A sine theta. Okay. All right. What else then? I need the Y material, right? I know some of it. AP, I should know. Well, no, it's not AP. I know it. It seems like I know AB. Okay, I know the AB. This distance right here from A to B is the same as this distance from C to D, and C to D is just the radius. Okay, so I know that AB is just equal to A, and then I need to figure out what the heck AP is. To figure out AP, I go back to this picture. Okay, so I note BA is just equal to the radius. Then this other distance I need, what was AP? From this diagram, AP is here. Okay? So I must be going after what? Well, AP is equal to the cosine of this angle here, which is 180 minus theta. So AP all over A, adjacent over hypotenuse, is equal to the cosine of 180 minus theta. If you go through the formula for cosine of 180 minus theta, that's cosine pi cosine of theta. Cosine of pi is -1, so it's negative cosine theta, and then plus sine of pi, cosine theta. Sine of pi is 0, so it's just going to be negative cosine of theta. And then you could solve for AP. So AP must equal negative A cosine theta. Okay. All right, so those are our formulas then. And hopefully I didn't butcher it too fast, but you know, these are my practice lectures, so I'm sorry if I messed it up. I don't want to have to start practicing for my practice lectures. I'm going to put another video up for my practice of the practice lectures for my class lectures. So I'm sorry if this is a little long-winded. In class, you know, I go a lot faster, so I cut out all the baloney. But anyways, at the end, our parametric equations, the long and the short of it, we have x is a theta minus a sine theta, and then y is a plus ap, which is minus a cosine theta. All right, and that's it. All right, great. So we'll see you next time. Thanks for bearing with me if you actually did. Sorry I butchered the parametric equation right there. Sorry I kind of butchered that last the cycloid thing. But it's all in there somewhere. The pieces are there. We just have to put it in right. I'll put it together in class for you. All right, I'll see you. Bye.